So what we're going to do today is we're going to take this unit circle to the next level. Pretend that looks like a circle. What we're going to do is we're going to actually do a graph of y equals sine x. What is the largest value of sine? Positive 1. What's the smallest value? Negative 1. So our graph on the y-axis up and down goes down to negative 1 and up to positive 1. Since most of our benchmarks happen to be the 90-degree marks, let's label this out at 90-degree intervals. At 0 degrees, what is the value of sine? 0 degrees is right here. What's the value of sine? Careful. Sine is this direction, right? Sine of 0 degrees is 0. As we go up to 90 degrees here, what's the value of sine? 1. So at 90, it's 1. But you'll notice as it goes up, it starts to increase really fast here. But then it's increasing, remember, look at the distance above. It's increasing really fast here, but it's getting slower and slower and slower until it levels off. So it makes a curve here, looks like that. Then at 180, it's back down to 0. So that curve continues like that. And notice it's pretty steep here. It's almost straight up and down there. In fact, it kind of is for a single moment. It actually is straight up and down. As we continue past 180 at 270, what's our value? Negative 1. Same thing, goes down really quickly and then it starts to level off. Then at 360, it's back to 0. Now 360 is equivalent to 0 degrees, which means this whole thing just starts over again. You guys worked with the oscilloscope at all yet? Yeah. So you've seen this, of course, this is called a sine wave. This is the basic sine wave. Again, just y equals sine x. Some parts of this wave that we want to talk about. One is amplitude. Amplitude can be measured a couple of different ways. We're going to measure it from equilibrium, or from 0 to peak. So that's our amplitude. There is something called peak to peak. That peak to peak distance is just 2 times our amplitude. So here we have an amplitude of 1. Our peak to peak, of course, is 2. Wavelength. It's the length to make a complete cycle. So pick a spot on the wave. I'm going to pick the peak here. The wavelength would be the distance to the other peak, the next peak. Of course, I could have picked, this spot right here where it's going down. Wavelength would have been the distance to that same spot where it's going down on the next wave. That wavelength would be the same no matter where we measure it. In this case, that's 360 degrees, or complete cycle is our wavelength. Now, something that really isn't shown on this graph is something called the phase. Phase is where in the wave that it starts. I'm going to actually label this as starting location in the wave. This wave starts at 0 degrees. Many of our other waves have a phase shift. And a phase shift moves 0 degrees to another location. And we'll look at that as we go. So let's look at some different things that can be done with our sine wave. Just making my graph quick. And our basic y equals sine x, as we said, goes up to 1 at 90 degrees, back down to 0 at 180, down to 1 at 270 degrees, back up to 0 at 360, up to 1 again at 450, and keep cycling. We keep going like that forever and ever. What happens if we do something like this? Y equals 2 sine x. Yeah, at 90, this is going to be 2 units tall. Because whatever value sine is still 0 at 0 degrees. 2 times 0 would be 0. But at 90 degrees, the sine is 1. Well, 2 times 1 is 2. At 180, the sine would be 0. What's 2 times 0? 0. At 270, the sine would be -1, so times 2 would be -2. 360, back to 0. So what we see here I didn't draw my graph real well here at all, did I? Is all that number here that in front of the sine does is it increases the amplitude. The amplitude was 1 for y equals sine x. Now it is 2. How about this? What would this one do? Y equals -3 sine x. Okay. It's 3, so it makes the amplitude 3, but since it's negative, it flips the wave over. So instead of being at a +3 at 90 degrees, it's at -3. Giving us that wave. So it still changes the amplitude, but it can also invert the wave or flip the wave over. Any questions there? Oh, I suck at drawing. There we go. So there's our sine wave again. Y equals sine x. This time I'm going to try to change something different. Notice there's nothing in front of the sine this time, so our amplitude is going to be 1 still. Now, though, I put it as 2x, sine of 2x. What's that going to do? Well, now, if I make a table here, let's say x is 45 degrees. Well, it's not sine of 45, it's sine of 2 times 45. What's 2 times 45? 90. So at 45 degrees, it's going to act like it's at 90, which is right there. At 90 degrees, x is going to be 90. What's 2 times 90? 180. It's going to act like 180 degrees, which is going to be right there. If I kept going at 180 degrees, it's going to act like it's at 360. So notice it makes, in the normal span of a single cycle, it makes 2 cycles. This is called the frequency. There's a relationship between the frequency and the wavelength. The frequency times the wavelength equals 360 degrees. So if this has a frequency of 2, the wavelength is going to be 180. Makes sense. Wavelength is right here. That would be one complete wave. That is only 180 degrees. So let's look at y equals sine 3x. How many cycles are there going to be in 360 degrees here? 120 will be the wavelength. The frequency is 3, which means there's 3 cycles in 360 degrees. So this is 90, 120 is going to be somewhere in here, right? That's a full cycle. So it's going to look like this. And then 240 is going to be somewhere in here. Oops. There's our wave. We got 3 complete waves in 360 degrees. So you can think of that number as either being the frequency or adjusting the wavelength. So 360 divided by that number is our wavelength. So I want you guys to try to graph one. See what you come up with for that. So first of all, how many cycles are there going to be in 360 degrees? 4. We got a frequency of 4. So I'm going to take 360 degrees divided by 4. Means that each cycle is completed in 90 degrees. So here's 90, 180, 270, 360. That's a full cycle. Remember, it goes back to 0 halfway in between each of those even. Next, let's look at this number, the -3, means, first of all, the 3 means the amplitude is going to be 3. Negative means it flips over. So instead of going up to 3, it goes down to -3. Now remember, it has to be back to 0 here. It's got to make a full cycle before it hits 90. So -3 is going to be here. And back to 0. Up to +3. And back to 0. There's one complete cycle. And I'm assuming you guys can continue that. Well, so those are what we can accomplish by multiplying. You could probably guess what would happen if we did this. Anybody want to guess? Well, what's that 1/4 mean there? Amplitude is only goes to 1/4. So it only going to go up to 1/4, down to -1/4. What's the x over 2 mean? Now we can think of that as 1/2 times x, which means every 360 degrees is only half of a wave. Or we can think of it as 360 divided by 1/2 means a 720-degree wavelength. So that means instead of being at 90, our first peak is going to be at 180. So in 360 degrees, that's all you're going to see right there. This is that first top. And it's going to go like this, and my graph is a little short. It's not going to quite come back to 0 on my graph. It comes back to 0 at 720 degrees. There's a full cycle. Any questions? How about this? What this basically means, going back to our table here, 0 degrees is going to behave like what? 90. So 0 degrees is going to be 90. I'm going to label this only goes up to 1. So it's going to be right there. It's going to behave as though it's 90. What's 90 degrees going to behave like? 180. Well, that'd be back to 0, right? 180 degrees will behave like 270. Well, 270 is where we had our valley, our trough. Down to there. 270 is going to behave like 360. And then 360 will behave like 450 or 90 again, right? So you can see basically what's happened here. If we look backwards, going that way, this is really the 0 point of our wave, right? What 0 ended up, we ended up tapping into the wave starting at 90 degrees and using 90 degrees as the 0 point. All we've really done is shifted our wave 90 degrees to the left. What do you think is going to happen then if I do y equals sine of x minus 180 degrees? This was plus 190 shifted at 90 degrees this way. Minus 180 is going to do what? Your zero is going to be at 180 degrees. So this is where our wave would normally start, looking like that. Oops. A little less lopsided than that. So then we just work our way backwards to get back to zero. It'll be like that. Does that make sense? Oh, good point. What's that one going to look like? Zero is going to be at 270 right here, right? Yeah, why? Because 90 and 270 add up to 360. So you can always convert. I could take this negative 270 and I can add 360 to it. That's the same as being a positive 90. Heck, I could take this positive 90 and add 360 to it. What's 90 plus 360? 450. Guess what? Y equals sine of x plus 450 is going to be that same curve. Remember we talked about that co-terminal angle a little bit last chapter? Well, 90, negative 270, positive 450 are all coterminal angles. They tap into that sine wave at the same spot. Because remember, it's still the unit circle. So each of these is just from 90 to negative 270 is just one complete wrap of the unit circle. We end up in the same spot on that unit circle. Here's 90, here's negative 270. We're at the same spot. Positive 450, we're at that same spot. Does that make any sense? So how about this? What's different about this one? Hey, yeah, it's outside the parentheses. I basically treat this as y equals sine x and then add 2 to everything, right? So if I had my y equals sine x here, it would look like this. If I add 2 to everything, well, starting here with 0 plus 2. It'd be at 2, right? This is at 1. What's 1 plus 2? 3. What's 0 plus 2? 2. What's negative 1 plus 2? Positive 1. 0 plus 2 is 2. All I did was move the whole curve at every spot up 2. So what would happen if I did this? Oops, helps if I put the sign in there. There. Well, let's see. We're going to start with our phase shift. So starting at 0, we're going to start at what would normally be negative 90, right? So our 0 point is going to be a positive 90. Basically, what we're doing is this. We're taking that, what's inside there, and we're solving it for 0. X minus 90 equals 0 means X is going to start at 90. You add 90 to both sides. So we start at X equals 90. We haven't changed the frequency at all. There's nothing multiplying the X. So our wave starts and goes like this. What's our amplitude? -2. Good. So we're going to go down first. Notice I'm sketching it out just a little bit. Oops. Because now I still need to account for -1 there, which means everything shifts down 1. Now we're looking at this and seeing that this is labeled 90, but really that's my 0 point. This is really 90 degrees, 180, 270, 360. Oops, no it's not. I gotta work backwards. There's my actual scroll. I was going the wrong way. So what would normally be 0 has to start at 90 degrees, then we've got to work our way backwards to connect back to this. These are going to take a while to get used to. We're going to spend a couple of days on these. So if you're confused on them right now, Jordan, hang in there. We still have to add in the cosine wave as well, which is coming. For right now, in that packet I gave you, page 363 to 364, 1 through 23, the odds, don't do any that are labeled cosine, only do the ones that are labeled sine. This thing I just did right here, by the way, is going to come in. It's going to be very important as we go to combine some things. Like if I had y equals sine of 2x plus 90, this is no longer a 90-degree shift. Why? Well, because it's 2x. 2x plus 90 equals 0. You solve that for 90, x is behaving like -45. Or sorry, solve that for 0, you subtract 90 and divide by 2. X is behaving like -45 degrees at 0 degrees. We'll go over more of that tomorrow. So again, just do the problems that deal with sines, page 363 to 364, 1 through 23, the odds.